Double sideband suppressed carrier. Name is what? Carrier is suppressed. And what it will be difference between this amplitude modulation, what we have seen in the normal, and this double sideband suppressed carrier, you'll see that carrier will not be available so that we can save the power. And here we are going to see that how we are able to generate the DSB-SC signal modulated wave, as well as how we are able to detect DSB-SC signal in the receiver sections with the help of balance modulators and ring modulators that we are going to see for the generation. And again, for the receiver section, we are going to see even Costas Receiver also. So still, if you didn't subscribe our channel, please subscribe it, share with your friends, like and write your comments, whatever your needs are there. So if you see that in case of normal M, the modulated wave is given as, what is the equation? AC 1 plus, we have Ka into M of t, and here outside what we have? Cos 2 pi fct. Here we are taking as the carrier signal as the AC cos 2 pi fct, and message signal is what? M of t. So here what we are seeing that this second term is having message signal, but first term is completely carrier signals. And we have seen the spectrum also. Okay. So that is when we are going to transmit the our modulated wave along with carrier signal is also available. So due to that, we have wastage of the power. So that power we can save in case of DSB-SC, and both side bands will be available, upper side bands and the lower side bands. So in case of DSB-SC, only second term we are going to utilize. So you see that second term is the what? It is the product of message signal and the carrier signal. So now our aim is that we have to design the modulator that will produce product of message signal and the carrier signal. So if you see that this is the envelope of DSB-SC for the particular baseband signal, and baseband signal is what? It is the message signal or modulating signal. And carrier signal here what we are taking? AC cos 2 pi fct. So it is same if you see that how we have in case of linear modulation, but here we have to obtain the phase reversal. Whenever if you see that this envelope is going to cross the zero line, okay. So what was the tendency of the modulated wave? If it is coming from the positive to negative side, it will turn the positive side itself that you are seeing here. Similarly, again this portion, okay, now it should go down, but due to phase reversal, it is turning in the same side. So here we have important phenomena that is called as the phase reversal also. Okay, so phase is going to reverse. So that is sometimes maybe they'll ask question also, what is the phase reversal? Objective question. Okay. And if you see that frequency domain of this modulated wave, so this is the frequency that is Fourier transform of this message signal m of f minus fc and plus m of f plus fc. So this thing already we have seen in case of normal AM modulation also. And if you see now this a spectrum, so here message signal or baseband signal is considered of the bandwidth 2W. Okay. Now if you see in case of a spectrum, so here we have Fc plus Fm this part, or here you can write Fc plus W as per this Fc minus W. Similarly here minus Fc plus W minus Fc minus W. So here you see that for the around the carrier frequency for the negative also bandwidth is 2W, and for the positive also we have 2W. But here if you see that this portion carrier is suppressed. What was available in the normal AM modulation, that is not available in the DSB-SC. Here carrier is what? Suppressed. So we are able to save the power. Now, if they're asking you about time domain, frequency domain representation, so that previous what we have explained now with that you can see. Now, if the question is separate, write about the generation or explain about the generation of the DSB-SC signal. So there may be name will be given like balance modulator or ring modulator, or as per your syllabus, you see that whether you have balance modulator only or you have ring modulators. Okay. So our aim, either we have balance modulator or ring modulator. What is our purpose? We have to generate the product of message signal and the carrier signal. So first we are going to see the balance modulator. Name itself is what? Balanced. So how we are going to balance? When we have two things that we are going to balance. So here we have AM modulators. So two AM modulators are used. This we can say AM modulator 1. This is the AM modulator 2. And M of t in one AM modulator, direct M of t is given as the input, whereas in case of second AM modulator, minus of message signal is given as the input. And both modulators are given same carrier frequency, AC cos 2 pi FCT. So the output of first modulator, what we'll have here? AC 1 plus Ka into M of t cos 2 pi FCT. Since here message is given, that is M of t, whereas the output of the second modulator, what we'll have? AC inside the bracket 1 minus Ka M of t. Since M of t is here, minus into cos 2 pi FCT. So now here if you see that this both output S1 and S2 is given to this summer here. So S1 of t and having one having plus sign and then having minus sign. So here we'll have S1 of t minus S2 of t. So due to that, what is going to happen here? First term will get cancelled. Second term will be only available. So that is how balance modulator is going to work here. And if you see that expression, what we have written earlier, same expression is here. So again, S of t is S1 minus S1 of t minus S2 of t. So that modulated wave we are going to obtain here 2AC Ka M of t cos 2 pi FCT. So if you see that apart from the 2 Ka, remaining all things is the product of message signal and the carrier signal. So this also can be written as like suppose 2 Ka into C of t into M of t. C of t is what? Carrier signal. M of t is what? Message signal. So now we got product of message signal and the carrier signal. Okay, that's why it is our DSB-SC signal. Another technique is called as the ring modulators. So ring modulator, another name is also double balance modulators. So that we are going to balance in the two ways. So if you see that here we have input side, we have a transformer. This is the center tape transformer. Here also we have center tape transformer. So two transformer is used here. Okay, transformer 1, transformer 2. The first transformer primary binding having input is what? Modulating wave. So this is our message signal. So that you can consider as per convenience. Like suppose we are going to consider AM cos 2 pi FMT for the explanation purpose. And carrier signal is given to through the center tape transformer. Suppose carrier signal we can take AC cos 2 pi FCT. So FC is the frequency of the carrier signal. FM is the frequency of the message signal. So here FC should be greater than FM, that you know. Okay, carrier signal frequency always should be greater than message signal frequency. So now when this waveform, we will see that when we have positive half cycle, okay, positive half cycle is going to occur for the cos here. So that is the carrier signal. So during the positive half cycle, if you see that only two diodes here, if you, white is called as the ring. First of all, if you see, white is called as the ring modulators. So we have four diodes, like we'll call the name 1, and this is the suppose 2, this is 3 and 4. So 1 and 3 is connected outer side, 2 and 4 is connected inside. And if you move in this all diodes are facing in the same way. If you go from A to B, again B to C, C to D, D to A, so all are positioning in the same direction. So that's why it is going to form the ring. So its name is what? Ring counter. So what is the operation? So here this carrier wave in this, okay? In case of ring modulator, this carrier wave we are not going to take as the sinusoidal waveform. So what we are taking the carrier wave here, we are going to take as the a square wave, okay? So carrier wave, what we are taking? A square wave. So during the positive of this square wave, if you'll see that square wave, how we are going to draw, okay, like this. So here in this situation, if you'll have, this is the reference line. So for the positive part of the carrier wave, diode 1 and 3 is going to provide the high impedance. During the, so that time what will happen? Diode 2 and 4 will be on. And during the negative part, diode 1 and 3 is going to be on and 2 and 4 will be off. Okay. So this is the carrier signal is here, a square wave. So when we have, if you're going to consider the ideal diodes, or when transformer is perfectly balanced, then outer diodes are going to switch off. Okay. So when outer diode is going to switch off, so it will have very high impedance, and then baseband signal, that is the message signal, is being multiplied by +1 during the positive of this carrier signal. And when we have carrier supplies the negative, then inner diodes are going to become off, and then baseband signal is multiplied by -1. This is the differential during the positive half and negative half. Positive half, outer diodes are off and message signal is multiplied by +1, and during the negative half, outer diodes are on and inner diodes are off, and message signal is multiplied by -1. So negative, so multiplied by -1. When it is positive, multiplied by +1. Okay. And finally, here we are going to get the product, that is the carrier wave and message signals. So here the waveform is shown. This is the modulating wave, and here a square wave is taken as the carrier signal, and this portion is the modulated wave, DSB-SC. So again, you can observe here phase reversal. So this square wave expression is 4 by pi summation n equal to 1 to infinity minus 1 to the power n minus 1 divided by 2n minus 1 cos 2 pi fct 2n minus 1. So finally, output of the ring modulator, it is the product of message signal and the carrier signal. So C of t is being multiplied by the message signal. And here if you see that whenever we have a spectrum, that is the odd multiple of the carrier signal, that is like FC, 3FC. Further again, when we'll get, when we have 5FC, and here -FC, -3FC, again we'll get for the -5FC. So only for the odd harmonic we have, okay, a spectrum only for the odd harmonic of the square wave. And baseband signal is limited by between the -W to +W, and carrier frequency should be greater than W. So remaining desired sideband, whatever we want to obtain around the carrier frequency FC, that can be obtained by the help of band pass filters. So particular frequency will be passed. So this is how we are able to generate the DSB-SC signal by the help of balance modulator as well as ring modulator, and ring modulator is also called as double balance modulator. Now we are going to see in case of demodulation. So modulation takes place where? In transmitter. After that, modulated wave is given to the over the channel. Then after that, we have receiver section where demodulation takes place. So now here our aim is that obtain the message signal components. To recover the message signal components from the transmitted signal is what here, modulated wave is what we have, that is a C of t into m of t. Okay. So like here C of t is our a square wave, m of t we can take as the sinusoidal waveform for the explanation purpose. And what is the requirement here? What is the frequency of the local oscillators? Okay, in the input side, same frequency we have to obtain from the local oscillator in the receiver side. So that is exactly coherent or synchronized, both in terms of frequency and phase of the carrier signal. So that's why its name is also given as coherent detection or synchronized demodulation due to synchronization between the local oscillator signal in the transmitter as well as receiver. So since we need to obtain only message signals, so unwanted signals may have high frequency, low frequency that we are going to see. So later you see that whatever desired signal we have that having low frequency components and unwanted signal having high frequency component. So now we have to use the low pass filter to obtain our desired frequency, and high frequency component will be removed. So this is the block diagram, okay, of this DSB-SC coherent demodulators. So we are going to use here product modulators and followed by the low pass filter. So S of t is C of t into M of t, that is given as the input to the product modulators, and we have local oscillators that having same frequency, only phase is their change, okay. So AC dash cos 2 pi ct phi. If you take the same phase, so that we'll see in the derivation that what type of the problem we are going to get. So here frequency, at least frequency should be must. Phase can be different. So that's why carrier signal is taken as AC dash cos 2 pi ct plus phi. So finally, it is given to product modulators. So here this carrier signal of this local oscillator is being multiplied with the S of t. S of t is the AC M of t cos 2 pi ct. So after multiplication, if you see, we are going to obtain AC dash cos 2 pi ct plus phi and cos 2 pi ct into M of t. So now here we are going to multiply and divide by 2 so that we can apply the formula of this one, 2 cos A cos B. So 2 cos A cos B formula is what? We have cos A plus B plus cos A minus B. So A plus B is going to be 4 pi ct plus phi and A minus B. So this 2 pi ct is going to get cancelled. So we'll get only 5 components here. So now if you see that in the two terms, first term having high frequency components and second term having low frequency components, okay. And here only we have attenuation by the factor cos phi. So we're going to prefer the second component here, okay, half AC dash cos phi m of t. So first term having, that is the carrier signal with 2fc. So that is high frequency components. So that's why we are going to apply the filter, so that after filter only second term will be passed and first term will be stopped. So that filter output V of t will be half AC dash cos phi m of t. So cos phi is your factor, attenuation factor here, by which wave is being attenuated. So cos value is maximum when it is the 0. Cos 0 is what? 1. So that's why when phi is going to be equal to 0, then it will have maximum amplitude, and when phi is going to become plus minus pi by 2, so cos pi by 2, it is 0. So that time its value is going to become 0. So now this 0 demodulated signal at this one represent the quadrature null effect of the coherent detectors. So maybe question will come also about what is quadrature null effect. So when phi is going to become plus minus pi by 2, okay. And this phase error cos phi is going to attenuate here the signal. So it is important we have to maintain the local oscillators, have proper synchronization in terms of frequency and phase with carrier signals to generate the DSB-SC. So this is the spectrum. You have 2W of bandwidth here, and here you see that we don't have component of how we have in case of in case of N. So this is the how we are going to obtain. Now another is the Costas receiver. Coherent is more popular. Another is the Costas receiver. So in the Costas receiver, if you see that block diagram, so it has two coherent detectors. Like we have only one coherent detector, what we are using? Product modulators. Since DSB-SC is what? In generation also, it is the product of message in the carrier. So now here also we are using the product modulators, and that is one of the input was the modulated wave. Another input is what? Carrier signal from the local oscillators. So this is the signal which is being transmitted. Okay. So now here we are going to talk about in phase and the quarter part. So if you see the block diagram, it will be much clear. Okay. So here, if you see that two product modulators are used. That's why we are telling you we have two coherent detectors, one product modulator 1, another product modulator 2, followed by the low pass filters, followed by the low pass filter here, and one is the local oscillators. So we will see that it has combination of coherent detector 1, coherent detector 2. So this is the transmitted modulated wave, AC cos 2 5 into m of t. Here we are considering, and we have voltage control oscillator that is called as the VCO. So now one modulator, what is the difference here? One modulator having a carrier signal cos 2 pi ct plus 5, whereas another modulator having carrier signal with minus 90-degree phase shifter. So due to this is going to become sine 2 pi ct plus 5. So after the low pass filter, as we have seen earlier, in case of coherent detectors, output is what? Half AC cos phi into m of t. This is the output of the coherent detectors. So here only function is the sine. So this is the output of the second half AC sine phi m of t. Now it is, if you see that it is in case this is whatever is being generated by the local oscillator or VCO, if it is same as the phase here, then this in channel itself is going to become the demodulated signal. If it is not going to occur, so in that case, we are going to consider the Q channel also, and both is given to phase discriminators. Now, phase discriminator is trying to adjust that error. Okay, and then again in channel will be the demodulated wave here, and it have negative feedback system. Okay, so local oscillator synchronized with the carrier wave, and here Q is for the quadrature. This part is same what we have explained. It is the low pass I channel is the in phase. Okay, so now if what is written, if local oscillator output is same as the phase carriers, AC cos 2 pi ct. Then what will happen? I channel output itself is the demodulated wave, and Q channel output will be 0 due to quadrature null effect. Now if it is having phase shift by, they're both going to change by phi. Local oscillator having phase drift by phi. Then what will happen? I channel output will remain unchanged, but Q channel is output is proportional to the phi. Now this both output of this coherent detector is given to phase discriminator. Name itself is what? Discriminators. So now this discriminator having a DC control signal, so that is going to correct this phase error automatically, okay, in the voltage control oscillators. So like this, how we are able to obtain this demodulated signal by the help of coherent detectors. And here you will see that what we have, Costas receiver. So these are the discussion about complete DSB-SC, and here we are able to save the power since AC is not available directly. Okay, it is in multiple of message signal, but separate term is not available. So we are able to save the power. Any doubt is there, you can write in the comment box. Thank you. Thank you very much. Like, share, subscribe.